Hello everyone, today I'm going to be explaining about the process of making soap and some chemistry around soap, so let's get right to it. To make soap, you're going to need some sodium hydroxide, water, oil. I'm using palm oil for this soap, but you can use or mix different types of oils for varying results. A soap mold and some soap additives. I'm using mint essential oil and blue food coloring for this soap. There are two main processes when creating soap, a cold process and a hot process. There are pros and cons for each process, but for this soap, I'm going to be using the cold process because it's more straightforward. So first of all, dissolve your sodium hydroxide in the water you prepared. The amount of sodium hydroxide can vary for each oil type, so make sure to calculate yours carefully before proceeding to the next step because too much sodium hydroxide can be dangerous for the soap to be used. I'm using the recipe from the site called soapguild.org. They have a really useful lye or sodium hydroxide calculator to calculate the amount of lye needed to make soap from an amount of oil. When making soap, it's usual to use less sodium hydroxide than needed because if you react all the oil, the end product wouldn't lather as easily. This method is also called superfatting. Also, when you are dissolving sodium hydroxide in water, be careful not to boil the water off because dissolving sodium hydroxide in water releases heat. As you can see, I'm placing the sodium hydroxide solution on an ice bath because it was heating up way too much and I don't want the water to boil off. Also, for the next step, it is important for the water to be at room temperature for this cold process. The next step is to add the sodium hydroxide to the oil. The reaction that is going here is a base catalyzed hydrolysis of the ester bonds in the oil, or saponification for short. So oil is almost entirely made out of triglycerides. A triglyceride is three fatty acid molecules that is bonded to a glycerol backbone. They have these ester bonds that are holding these two separate molecules, and it is quite a sensitive bond, and when you add a strong base like sodium hydroxide, it will hydrolyze the ester bond and break it to an alkoxide group and a carboxylic acid group. The alkoxide group is really basic, so it pulls the hydrogen from the carboxylic acid to become an alcohol group. The remaining carboxylate group then forms an ionic bond with the sodium. To create, well, for our case is sodium palmitate. For the base, usually people use alkali metal hydroxides like sodium hydroxide and potassium hydroxide because they form salts that are usually more water soluble than their other counterparts. Sodium hydroxide usually creates a harder soap, so it is usually used to create bar soaps. For liquid soaps, people generally use potassium hydroxide as it creates a softer soap. Since I'm using palm oil and sodium hydroxide for this one, the major molecule that will be created is sodium palmitate and also sodium oleate. So back to the mixing. After pouring the sodium hydroxide solution, immediately mix as fast as you can. Some people recommend a hand blender, but I'm not making very much at the same time, so I can stick with hand mixing this. After mixing it for some time, it will reach a point called trace. Trace happens when the water and oil forms a stable emulsion, since enough of the sodium hydroxide has reacted with the triglycerides to create sodium palmitate in our case, which is an emulsifier. There are different levels of trace: thin, medium, and thick. Thin trace is usually very liquid, but it has already formed a stable emulsion, so the oil and water won't separate. Medium trace is quite thick, but not thick enough to hold its shape. Thick trace is very thick. It will hold its shape even when left undisturbed. Each trace has its purpose, but I'm going for a medium trace for this one because I'm only looking to add some coloring and smelling additives, and also because it's easier to place in the mold. After it has reached trace, you can start adding your additives. The reason you add the additives after trace is because the sodium hydroxide has reacted with a lot of the triglycerides, so it won't destroy the additive you add that aren't compatible with sodium hydroxide. Also, for some reason, my blue food coloring made the soap purple when in fact it should have been green because yellow from the oil plus blue from the food coloring would equal green, but instead I got light purple. First I thought this food coloring degrades from pH, but it definitely wasn't the case because I tried dripping the food coloring in some basic solution and it didn't change color. So I would need to research this more. After mixing it thoroughly, you can place the soap in the mold. The curing process would take a day, but for the soap to be usable in the cold process, it would take 4 to 6 weeks for the reaction to reach completion. The next day I demolded the soap and it looked like this. It honestly didn't look so bad in the end and it turned out quite well. And now I'm going to demonstrate to you that water can't ever mix with oil. As you can see here, I have a small glass filled with oil and water. As I added the soap in the glass and mixed it, it looked like the oil and water is mixed. But actually it isn't the case. Emulsifiers are molecules that are amphiphilic, meaning they have a hydrophilic or water-loving head, and a lipophilic or fat-loving tail. And it's why all emulsifiers can bond with water and oil at the same time. The hydrophilic head, which is polar, can bond with water using hydrogen bonds, but the lipophilic tail is non-polar, meaning water can't and doesn't want to bond with it, and because of that they push the molecules away. Since the water pushed the lipophilic tail away, they start to meet each other and create this small sphere called a micelle. This micelle is why it looked like the oil could dissolve in water, because the oil is safely separated from the water inside the micelle and is evenly dispersed in water. This evenly dispersed micelle makes this a colloid and not a solution. You can easily destroy the micelle by adding some acid. If the pH is dropped, the potassium, since this is a liquid soap I'm using, will react with the acid and the carboxylate group in the soap becomes a carboxylic acid group. This carboxylic acid group of a fatty acid isn't as water-soluble as its alkali metal carboxylate counterpart, which means the soap has lost its amphiphilicity and it will become just like any other oil. The top part of the separation is usually called scum in layman's terms.